Hi everyone, my name is Rita Sousa. I'm an assistant professor in civil engineering. In my research, I use several machine learning techniques to address problems in topics that range from subsurface characterization, land subsidence monitoring, and tunneling. And so today I'll be presenting some of my work on tunneling. So the use of underground has been gaining more and more importance as surface land becomes scarcer and scarcer. And even though putting entire cities under the ground may be a little bit too futuristic, the use of subsurface is already playing an increasingly significant role in the functioning of future cities when coping with current and future challenges of urbanization and densification. And this is particularly true for multi-layer networks of underground infrastructure systems, especially for mass transportation, as the ones that you see here in the figure. And it is certain, or we believe that the number of these systems and the complexity of these systems will increase with the ever-increasing population and urbanization. The major issue is that the existing tunneling methods, such as TBMs, that's what I'm going to be talking today, are often inefficient to accomplish some of these complex projects. They are very slow and they are riddled with risks. The main reason for these tunneling inefficiencies are unexpected ground conditions, are the fact that we don't know for certain what's under the ground, right? And this results in higher risks during construction. And even though recently have been efforts to improve existing TBM technology, characterizing and forecasting ground conditions with very limited knowledge of what's underneath the ground is still one of the most formidable and challenging tasks that you can have in tunneling. So trying to figure out ways to predict what's under the ground in the context of tunneling has been one of my passions for many years. And that's what I will be presenting here today, which is the application of machine learning techniques and AI techniques to ground prediction during tunnel construction. And I'm going to do that by using a real case study of the Porto Metro in Portugal, since that's something I've worked on. So trying to figure out, just want to get my pointer. So trying to figure out, so the main challenge in tunneling comes from the design phase. And where you're estimating ground conditions and ground profiles. This is a tunnel. Here, this is the Porto Metro tunnel. And you're trying to estimate the ground profiles, the ground that the tunnel is going through basically a limited number of sampling points, such as boreholes, which are vertical wells that are spaced every 100 meters, every 200 meters. And you have to basically guess what's in between. That results in ground profiles that are highly uncertain, that are determined by engineers during the design. That is one challenge. So when you start construction, these are the ground profiles that you have, and they are quite uncertain. The other challenge is that it comes from the construction phase, is that TBM operation relies heavily on human operators and their ability to change or to predict changes or to sense changes in the ground. And these practices normally lead to significant inefficiencies, delays, cost overruns, and sometimes accidents during construction. And this is an example of something that can happen when you run into unexpected ground. This is a picture of an accident that occurred during the construction of the metro of Lausanne in Switzerland, where they run into unexpected ground. So before getting into the details of the methods that I proposed, I wanted to show what a TBM is, right? So this is a sketch of a TBM. And modern TBMs are really highly complex machines where many processes happen at the same time, including drilling, grouting, installing the lines, many other processes, just like almost like a factory, a moving factory. There are different types of TBMs, and this one that you see here, which is the one that was used in the construction of the Porto Metro that I will show you, is called an earth pressure balance machine. In this method, the soil is, or the ground is broken down by beats that are installed in the cutter head that and then the broken down material is pressurized here inside this excavation chamber, and it's used to support the face. And then the material is extracted through this screw conveyor onto a conveyor belt where it's weighted and then taken to a repository. During the operation of these machines, the TBMs record hundreds of parameters every 10 seconds. So the TBMs are equipped with sensors that are capable of recording large sets of data. And what we have here on the right are some of the most important recorded data sets. So based on the profiles, on the ground profiles that I show you that are determined during the design phase, thresholds for the TBM operational parameters are set for different zones of the drive of homogeneous ground conditions. These thresholds are upper and lower levels of several main parameters that, and what the operator must do is to try to maintain the pressures and some of the operational parameters within those set thresholds. The problem with these thresholds is that they are based on ground profiles that are determined during the design, and therefore they are riddled with uncertainties. Right? This is an example. This is an example of the data coming out of the Porto Metro TBM. This is the record of the earth pressure sensor of one of the sensors installed in the TBM. In addition to that, material that is coming out of the TBM is also weighed and inspected visually. And so what you see here is the operator visually inspecting the material coming out of the TBM. And here on the side, you can see the inside of the TBM and the mock disposal system. And you can see how complex this type of machines are. So what happens is that most of the operation of this equipment, of this TBM, relies on human operator. And effectively, this operator is only able to manually monitor no more than 3 or 4 parameters at a time. So the rich set of data that are produced by the TBM sensors, remember these are about 200 parameters recorded every 10 seconds, are still not being systematically used to forecast or to try to forecast ground conditions ahead of the TBM phase. And therefore, proactively try to adapt the machine operators so that you can go faster, cheaper, and possibly avoid any accidents. So even though the TBM technology has been improved considerably since inception, there's still enormous need and potential for progress in this field. So most of my work has been in trying to predict geology ahead of the tunnel based on observations from machine performance, so from these sensors. And the ultimate goal is to create a methodology that will lead to full automation and digitalization of tunneling construction. So what I'm going to present is one of the earliest models that I developed, and it's been applied to the Porto Metro. And it aims at predicting probabilistically geology ahead of the TBM. And it uses a dynamic Bayesian network, which is an AI technique, that has the advantage that you can model parameters that can be learned from data and from experts. So you can do a combination of both, which is very important in this field that I'm in. So in order to understand the model, you need to know what a Bayesian network is, and I'm not getting into a lot of details, but just going over briefly what it is a technique used in many problems in artificial intelligence where you need to reason under a certainty. It's basically a probabilistic graphic model that represents a set of variables, and the sets of variables are here represented by these nodes. This is a generic BN. And attached to these nodes are probability or conditional probability distributions. You also see several edges that represent the conditional dependency between all of these variables. So Basically, a Bayesian network represents a joint probability between a set of variables in a compact and factorized way. It takes advantage that not all of those variables depend on each other. And what you have here is basically the mathematical representation of the graphical representation of a Bayesian network. Now, Bayesian networks that model sequences of variables are called dynamic Bayesian networks. And this is this dynamic Bayesian network that you see here is also the typical structure of our ground prediction model. The process that you're trying to model is normally divided into slices that can be time steps, or in the case of our tunnels, they are sections. For our particular model, I have two types of random variables. The yellow ones, which are the ground classes, that's the ground, that's what I'm trying to predict, that's my output. And then you have these blue ones, which are the observable construction variables. So to fully specify this dynamic Bayesian network, you need to specify a transition model that represents the probability of going from one ground class state to another ground class state, and an observation likelihood model that represents the probability of observing a certain output, basically observing a certain recorded parameters of the TBM, right, torque, penetration rate, etc., given that you're going through the particular ground. So this is how the inference works in a dynamic Bayesian network. You observe construction at section 1, and then you predict geology ahead of the phase at that section, and then ahead of the phase. And then as the tunnel progresses, the same steps are repeated. Okay. Once you know your ground classes, you can do basically anything with that, right? You can do risk analysis. You can optimize the operational parameters of the TBM. That's really what's at source of that problem, is knowing what are the ground classes. So I'm going to demonstrate the capabilities of this model through a case study that I was heavily involved in. So in 2000, they started the construction of the metro for the city of Porto, which is the largest city in Portugal and one of the oldest city centers in Lisbon, in Europe. And two of those metro lines have tunnels that run beneath the center of the city of Porto, which is World Heritage, Tunnel C and Tunnel S. I'm going to focus on Tunnel C, and this is an interesting case because there were 3 accidents during the beginning of the construction of Tunnel C, during the initial 300 meters. And this has provided us an opportunity to test our geological prediction model. Would we be able to predict changes in geology, and would we be able to do that early enough that we could predict, that we could potentially prevent some of these accidents, right? I've shown you this before. This is the geology along Tunnel C. Consists mainly of, the tunnel went through both soil, mixed ground, and rock, so all types of geologies. I'm gonna go quickly here, but I just wanted to show you a view of the actual machine that drilled the tunnel. On the left, you have the view of the TBM arriving at Trindade, which is at the heart of the old city of Porto. On the right, you see the TBM arriving at the at Aliado Station, which was built by a cut and cover. And you can see the TBM here. That's the shield. This is about 8 meters, 20 something feet. It's about 10 meters, 30 feet. And then behind you have a train of almost 200 meters that supports all of the operations that go inside the TBM, and the operator is inside the shield, controlling all of the controlling the parameters and adjusting the operational parameters. These are the photos of the sinkhole that was caused by the 3rd accident that occurred in January 2001. A building fell into a crater and caused the death of a person, unfortunately. And there was a site investigation that was performed after the accident in order to try to determine the causes of that accident. And what this picture shows you, and that's why I wanted to show you, is that if you think that so you have to know that the reds here are soils, and the greens and the blues are rock-like materials. So it was predicted, so the design ground is here, and it was predicted that the tunnel would go mainly through rock. What happened after the accident, when they put the boreholes in the ground, they realized that most of the material that the tunnel went through was actually soil, and soil is much softer and requires a different set of operational parameters than rock, right? So we wanted to use the Porto Metro to test our ground prediction model. We wanted to see if we could predict these changes in geology, if we can eventually come up with some warning that could come up with something that could serve as warning to potential tunnel failure, right? And so in collaboration with the Portuguese authorities, I was able to get special access to the data, and we got all the data that we needed: TBM performance data, geological data, accident reports, etc. We modeled that data, and we trained our dynamic Bayesian networks. We, because we're engineers and we know a lot about the mechanics of it, we decided to set set the model structures ourselves and only learn the probability distributions associated to each one of those links from the data. And we ranked, we tested many models, and we ranked them according to their performance. And actually the best performing model was a very simple one, but one that actually made sense mechanically. It had penetration rate, it had cutter force and cutter head force and cutter head torque, and all of those made sense mechanically, in the sense that this would give us an indication of what ground we're going through. We then applied this model to the first 300 meters of the tunnel. That data was never used in the testing, validation, or in defeating the validation or the testing of the model. We kept it aside because we didn't know what happened in those 300 meters, those initial 300 meters where there were several accidents. So we just kept that set of data aside, and we applied the model to those 300 meters. And that's what I'm going to show you here. All right. So I'll show you the results of the model in the accident zone. The lines that you see here, those lines, are probabilities of ground classes, G1, G2, and G3. We divided our ground into soil, mixed, and rock. And now this slide here shows you it just shows you the ground prediction model superposed with the results of the simulation. So do you remember what I talked a little bit earlier? We sectioned the model, and so in one section we observe parameters, and then we update this probability, and then we use this to update the probability of the ground class at a section, and then predict the head of the tunnel. The probabilities at each section corresponds to the output, so those lines correspond to the output of these green nodes. So what we saw is that at ring 264, which was the previous one, the tunnel was excavating through rock. And in this situation, persisted for several rings until you hit ring 281 or 82, where the situation changes and the tunnel starts to enter a zone of higher probability of mixed conditions. Up to this point, the strategy that was used to operate the TBM was that suitable for rock-like materials. Now we enter mixed ground. They continue to operate the TBM as if they were going through rock, right? You continue as you go along, this situation persists, and then, but you see that the probability of ground class 1, which is soil, starts to increase, right? It starts to increase until you enter the zone of the accident. And at this point, from ring 282 to the zone of the accident, the TBM should have been operating with different parameters, no longer with an approach for rock-like materials. All right. So what we saw was that the results of our geological prediction were in good agreement with the observations post accident. We were able to predict the changes in geology prior to the zone of the accident. In fact, we were able to see that things were changing 10 meters ahead, that's about 30 feet. That would have probably allowed them to stop the TBM if they needed, or even to change the operation mode. And I just wanted to give you a little bit of the picture. TBMs go really, really so slow. They are just like snails. So there's enough time to change the operational parameters. Okay, so do you have any questions?
Okay, thanks very much, Rita. It's awesome to see this gigantic TBM machines, right? Working and basically contributing to the significant infrastructure building in all parts of the world. Okay, so questions from the audience? Okay, if not, Rita, I have a question.
Yes.
So clearly your ground prediction model is based upon the instant sort of analysis of what is produced, right?
Yes.
Machine. And so that's great. And you can provide real-time adjustment of the operation parameters. So my question has to do with sensor technology that one could use even just prior to the whole project itself to map out the geological conditions along the route using ground penetrating radar, for example. So what's the state of the art these days?
Yeah, so you do have some TBMs that have geophysical measurements. One of the issues is for some particular techniques, you have to stop the TBM. You cannot use it in advance. Another one is that, you know, they are not a direct mapping. It's not that you can actually see exactly what's ahead of you. You have to go through a process of interpretation as well. So one of the things that we're trying to do now is to actually combine all of that information with the sensor data from the TBM. So use all of that information with the sensor data. But yes, they are not a one-to-one mapping. They are subjected to interpretation. There's also some challenges when it comes to using them while the TBM is functioning or while the TBM is driving.